Can you hear me? Can you hear me? Can you hear me? Can you hear me? Hello? Hello? Can you hear
Yes.
me?
Hello, sir.
So I'm going to start it. Wait a minute.
Sir.
I have put it recording. It is getting recorded today, I think.
Yes, sir. Okay.
Okay. Let me start. So that today we are starting sequences. Okay. So today we are starting sequences. First, if you take any non-empty set X, this definition, what does it mean? By a sequence in X. What is the meaning of that? X is any non-empty set. Not necessarily it has to be real or complex. An X sequence actually is a function from set of naturals. That the domain is always n such that you have this. The sequence is nothing but a function whose domain is n and the codomain range is x. So that if you have n, then here fn. Usually fn we denote by xn, because this indicates x that it is coming from big X, and n it is the function of the value of the function at n. So since it is countably infinite, so we can list it by like this. Usually we list the function like this. N belongs to n like this. That means you get xn, n belongs to n. So actually this we usually do not write. It is understood, xn. Okay, so that this is the definition of the sequence. Sequence is a function whose domain is set of naturals n, big N, and whose codomain range is x. That means elements of the sequence come from x, but it is a function actually. Okay, if you can ultimately, when you are doing analysis, whenever possible, you'll have to look at the thing so that you can have functions. This is the easiest way to look at the things. This is the easiest way. Okay, so sequence is nothing but a function that I have explained. Now, particularly if you have take x equal to r, real line, then we call this sequence a real sequence. If x equal to c, then we call it a complex sequence. See, complex numbers. Then we call it a complex sequence. Okay. Actually, often the study of complex sequence is not much different from the, actually is not different from the study of the real sequences, because complex sequences can always be divided into two real sequences. Like suppose you have this Zn. Zn is a complex sequence. So each Zn you can write xn plus iota yn, where xn, yn are real sequences. So this way a complex sequence can be split into two real sequences. So this is important to understand the theory of real sequences. Okay. Now what I'm going to explain on that, in fact many people even after studying so many years and that, they have, I do not think they do not understand the definition of subsequence properly. So subsequence, so you should understand that. Okay, subsequence, you say sub, like set, subset. So you make think of comparing with its sequence, subsequence. So that means you may, if you compare, you may think from the sequence, if I pick up some elements, infinitely many elements, that will give you a sequence. The answer is no. This be careful about this sum. Here, when we define a subsequence, we'll have to put a condition. You may say, why we are putting that condition? Because many results which we characterize in terms of subsequences, if we do not follow that definition, they won't be true. Then what is subsequence? Now look, first let me give you an example here. Like, we start with this sequence, xn equal to n. That means 1, 2, 3, 4, 5, like this. Okay. Now look, if I take odd numbers, 1, 3, 5, 7, this is the subsequence. But same thing is, suppose if I do it, first 1, then 5, then 3, okay, then 7, then 11, then 9. I'm picking up all the odd integers. But look, my order is something that here, first 3, then 5. Here 5, then 3. Here after 7, 11, then again 9. Now look, what is the difference? Difference is that here I'm following an order. In the sense, I'm always from the first one. You look here, the first one. I'm always moving to the right. I'm not coming back. Look, I have gone to 3, then I have gone to 5, then I am going to 7. I'm not coming back. That means I am always moving to the right. On the other hand, this sequence, look, he moved to the right, then he came back, then we are moving to left. After 5, you have gone here. Look, you have 1 to 3, 1 to 5. This you have gone. This is ticket. You are moving to the right, but then you came 5 to 3. Then again you are coming back. You are moving to the left. Similarly here, after 3, 7, 11, you are moving to the right, but the 11 to 9, that you are moving to the left. So here is the restriction, that when you pick up elements from a sequence, and if you want to construct a subsequence, you will be always have to move to the right. Move to the right. You have the freedom to choose the elements, provided you always keep moving to the right. You are never allowed to move to the left. If at any point, if you have moved to the left, that means you came back, you are not getting a subsequence. So this is not a subsequence. This is a subsequence. Now, how to put this definition? Okay, this is strictly I am going to the left. I am going to the right, moving to the right continuously. Okay, so how will you put it mathematically? Moving to the right. Look, when you move to the right, basically you're doing it in increasing order. Okay, so that, look, how I am going to define the subsequence. So suppose you have a sequence. That means you have a function f. This is a function. Now, if you want to have a subsequence, that means you will must have another, because this is the way you are picking up, another function phi here, which is strictly increasing. Not only increasing, strictly increasing. That means if you have m greater than n, it means implies phi m greater than phi n. Strictly, this is. That means m greater than n, if I write 5m greater than equal to phi n, I do not know whether equal, then it will be simply called increasing. But when you say strictly increasing, that means this, for all nm. For all nm belongs to n. This is called a strictly increasing function. If you have this, first you have a function. Now look, if you take composition, that means this, f dot phi. Now look, f dot phi itself a function from n to x. So this is a sequence. Now look, here domain n, if you take, it is coming f of phi n. If you look, use this notation xn, the fn was xn. That's the notation I used, we denoted. Then it will be actually x phi n. So that this f phi, this is called a subsequence. Subsequence of f actually. Okay. So that, now look, that means out of a sequence, if you want to have a subsequence, you must have like this a composition where phi is a strictly increasing function. So look, I can have many strictly increasing functions. Okay, strictly increasing functions is precisely the informal language. You are always moving to the right. You are not coming back. You are always moving strictly to the right. You are not even standing anywhere. Okay, you are moving to the right. That is precisely the meaning of moving to the right. You're not standing anywhere. So that precisely gives you the strictly increasing function. So if you combine them, you get another function on the domain n that is called a subsequence. Now that you should keep in mind. So whenever you are forming a subsequent, like the second example I have given there you are not, it was not strictly increasing function. Okay, it was a function, but it was not increasing function. Forget about strictly increasing, because you are coming back. So x phi n, usually we do not write this. We write this x k n. That means for phi we denote by basically k, and phi n by k n. So that x k n will be called a subsequence of xn. Okay. So that means here phi, we are calling it k. So n, phi n, you are calling k n. Okay. Here, be careful. This is k n I'm writing. Okay. Some people write it nk. That means they write xnk, a subsequence of xn. That means they are changing the notation. That means their phi, it should be k actually, because first it is coming k. Phi k is nk. That means their function is actually n. So it is a bit confusing, but it is also very classical. So, but you should be careful, whatever way in notation you use it, this or the previous this one, but I think this is more precise, okay, than this. But you should be careful. This gives you a, it comes from a strictly increasing function. Look here, that I explained everything here. Okay, in page 24, we will say look at this. Okay. Actually, this is what I am saying, that very specified way and that. So subsequence, always right. In fact, I have pictorially explained also that all these things and that. Okay. Now look, why you are insisting? If you don't follow this, then many of the results, first of all, some results you may get the wrong proof. And secondly, which is more disastrous, that you may get wrong results, in the sense apparently you get the results which are not true. Okay, if you say if you have a subsequence every sequence has some subsequence, then it follows. But then if you do not follow this definition of subsequence, that means either your proof is wrong or the theorem, the so-called result is wrong. And it happens. Okay, so that be careful when you are dealing with subsequence. This is the main thing. Actually, in practice, you can always find your sequence, you're having a subsequence. Only thing you'll have to check whether you are picking up a subsequence, whether you are moving to the right. If you are always moving to the right, then you are sure that you have picked up a subsequence. But if you have doubt that you are not always moving to the right, you should check strictly. Okay, so this I said in the end of the page 25, last two lines. So be careful while picking up a subsequence. You may land up with a wrong result or a wrong proof if you do not ensure that you are really using a subsequence of a sequence, not simply a subset of that. That means what I'm saying, this subsequence I'm calling it, it is not only a subset of this. This is subset plus some restriction, subsequence. That restrictions means strictly increasing function. The picking up. Subset, when you are having this, you can pick up elements. You have to pick up elements. You don't need to bother about how you are picking up the elements. But here in subsequence, you need to bother about how we are picking up the elements. Okay, right? So I think for the rest of this note, we will take x equal to r. So we'll be talking about real sequences. Okay, so that first let us have, now we are talking about real sequences because this is course in real analysis. Okay, right? So that first thing we talk about convergence of sequence, but before that we need to have some definition. Convergence, basically I need to talk about convergence of sequence. Okay, but before that we need to fix some definition. First definition I have written on the page 26, that the definition of neighborhood. I think you have done it in B.Sc. So delta greater than 0. So if you take this interval x minus delta to x plus delta, that means suppose this is your x and take a so-called open interval. I think it is not, length is coming same actually. Wait a minute. Suppose this. So this is x plus delta. This is x minus delta. So this is called a neighborhood of x. That means all those points here, basically in the real line, such that distance between y and x is less than delta. This is called a, we will call it a neighborhood. So this is called a neighborhood, because if you change delta, you get another neighborhood. A neighborhood. Of x. Now look, neighborhood, usually people use some sort of notation, either NBD or N-hood. Some authors, it depends on. So that I may use this thing or this thing, but probably I will use this one, N-hood, neighborhood. It is in the shorter form. It's mathematics, it's very accepted one. Okay. Neighborhood means this N here, B in the middle, D in the end. And neighborhood here, N here, and the last thing you are taking, hood. Okay, right. So this is a neighborhood. Okay. Now, the second definition that I said eventually. This is a very familiar, very favorite term in measure theory, eventually. Okay. Measure theory, they deal a lot with the sequences actually. Basically, they deal with the sequence, either sequences or sequences of functions. That I've explained in the note in the end. I think this note or the next note. I think next note I have explained. Sequence of functions. Okay, eventually. Eventually, matlab, you see that suppose you have sequence xn. Okay, and I said xn, when I say xn is eventually in the neighborhood, this neighborhood, in the neighborhood x minus delta to x plus delta. Look, I am choosing one neighborhood, so that when I say eventually, that depends on the neighborhood also. It means this neighborhood contains all the members of the sequence except finitely many, Okay, that means there exists n node belongs to n such that xn belongs to this neighborhood. Let me finish it. For all n greater than equal to n naught. It is if you write greater than equal to greater than, it doesn't make a difference. Okay. Now look, actually this neighborhood, there exists n naught. This will depend on delta, this neighborhood. I'm just eventually we will get a lot of examples. So this should be written as n delta. That means to indicate that this integer n, natural number n depends on delta. That means except finitely many. Look, only I'm not saying, look, that means x1 up to xn naught minus 1. Okay. I'm not saying they are not here. Some of them may be here. Okay, but I know after a while everybody is there. Look, simple example you take that xn equal to 1 by n. That means sequence is 1 by n. So if you take a neighborhood of 0, so take x equal to 0. Okay, so neighborhood of 0 will look like this thing, minus delta to delta. Okay, right. So suppose I give you delta equal to 1 by 10. Then you see that what happens. Then starting from, look, that means 1 by n, here x is 0, less than 1 by 10, that is in between that, if and only if n greater than 10. That means in this neighborhood, if you see that, minus 1 by 10, 1 by 10, it contains all the members of the sequence starting from x11. Before that, x1, x2, xn it is not here. So that we can say that here, that we say that this sequence xn is eventually in this neighborhood. Okay. Now look, what I said that this eventually will depend on this. Now I have taken delta equal to 1 by 10. But of course, if I take delta equal to 1 by 15, then you know that here you'll have to take what? It will start, the elements will start from x to the power 16, so that this n will change. For delta equal to 1 by 10, you could take n delta equal to 10. But for delta 1 by 15, you'll have to take n delta equal to, actually you'll have to take 16, because I have written greater than equal to that. You should be careful. If you write only greater than, you could take like 10, 15 like this. Okay, so that it changes. That means eventually it depends on, means that means for a fixed neighborhood I will get an integer. After that it will be there. Okay, not for all the integers it will be, for all the neighborhoods it will be the same integer. Be careful. Not for all the neighborhoods it will be the same integer. It will depend on the neighborhood. So this is called eventually. Why we are calling eventually? Because particularly in measure theory, it is very much required. Suppose you have a property, you have sequence xn and property p. I do not know what is the property in that. And when I say a property is eventually true, look here, that xn satisfies p eventually. satisfies eventually. P. This property P. It means like what? Eventually that except finitely many n, except finitely many n, this statement P is true. Now look, if I say P n, if I write, that means the statement P for n. So this means actually, and statement P for n, that means statement P for n is true. Suppose you write true. Statement P for n is true. I have written here. Then that means if you take this state eventually, that means if I write look, I am not saying this is true for all n. Now I am saying eventually. That means eventually means this thing. That means I will get some n naught such that Pn is true for all n greater than equal to n naught. Some n naught. But below n naught, it may be true, it may not be true. That I do not know. That I am not even bothered about it. The only thing what I'm saying eventually means after a while. That means we say also informally after a while. After a while, this is true. Okay. Like it had happened in the neighborhood, I say that. Okay. Like previous example I was taking, I said, how about this? Sorry, minus 1 by 10, 1 by 10. Here my statement will be how many members of the sequence are there here. All I can say after 10, everybody is there in this neighborhood. After 10, that means eventually it is in there. So eventually means except finitely many you are there. Then why you are talking about this? Because I am talking about informally. That infinite is a very vague word right now. So basically the behavior of sequence, it's actually you need to look at the behavior of sequence at infinite level. That means for finitely many integers you can always chop out. It doesn't affect the behavior of the sequence. It doesn't affect the behavior of the sequence. Okay. So that I given. Okay. Example I have given that I have taken xn equal to n. There, like here, first thing I said to take xn equal to n for all n less than equal to 10 and above this is 10. That means, look, it is eventually constant. It is not a constant sequence. It is not everywhere constant. Actually, in measure theory, you will get eventually. Actually, it is almost. Actually, it is they use the word almost and everywhere. That means for all n, basically. Okay. Look, this example I am giving you that it is eventually constant, not constant. So that look, eventually constant and constant. Look, eventually constant here I have given xn equal to n for n less than equal to this. Okay. And xn equal to 10 for all n greater than 10. And here I am writing xn equal to 10 for L. Look, this is constant because for whatever n it is 10. But here it is not like that. For n less than equal, that means for n less than equal to 9, it is coming 1, 2, 3, 4, 9. But after 9, basically, okay, because I have written that after 9, it is everybody is 10. That means it is eventually constant. So don't ignore this. Eventually, yeah, this is called in English adjective. In Hindi, it is called visheshan. What's going on? Understand? This is called constant. We are qualifying it. So this is adjective here. Basically, okay. You may say that if you know grammar bit well, is it adverb? It is not, huh? Is it adverb actually, or what I'm calling adjective? Okay, adjective. This is actually Sanskrit word. Okay, visheshan. Okay, visheshan means it is qualifying. You're giving, particularly you're specifying. Okay, right? So be careful. There is a difference between eventually and without eventuality. Now the convergence of sequence, look, vaguely, not vaguely, informally what I will say. No, I won't say vaguely. Now the convergence of sequence. Now the definition of that, the convergence that I said that. Because why we are concerned about convergence of sequence? Look, I have given you a sequence. Next thing will be to see that whether sequence converges. That's the definition. Means like here a definition. Xn is a sequence, and I say I have taken real sequence. Xn converges to X if, informally I'm saying, if every neighborhood of X, in every neighborhood of X, Xn, the sequence Xn is eventually there. Xn is eventually there. That means what I'm saying, every sequence, other way you can write, every sequence, here not Xn is eventually in every neighborhood of X. Now look here, eventually again I am specifying. That means if you change the neighborhood, that eventually, that depends on a number, an integer, that may change. Okay, eventually. Okay, that means if here usually a neighborhood I have taken X minus delta to X plus delta. Usually we take epsilon delta. There is a reason for that. If you in the undergraduate you studied the continuity epsilon delta, then you know that usually for what purpose you use epsilon and delta. Okay, so that doesn't matter. First you say, so this is interval. Now eventually I say this is here. That means there exists n delta. That means this again will depend on this. This depends on this means it depends on the neighborhood, because this neighborhood is of this form. That means the neighborhood will depend on delta, because only if you change delta then you get a different neighborhood. There exists n delta belongs to n such that Xn belongs to this thing, this neighborhood, for all n greater than equal to n delta. Here I have taken n epsilon, delta equal to epsilon. Okay, so that means what you are getting? That means actually you're getting Xn, difference between Xn minus X less than delta for all n greater than. This is eventually, because after n delta you are having this property. That is, eventually it is in this neighborhood. Eventually. Okay. So this is informally say that the sequence xn converges to x if it is eventually in every neighborhood of x. Eventually. In every neighborhood of x. Here. If for one neighborhood when it fails, then it is not converging. That I have written. A sequence xn in R is said to converge to a real number x if the sequence xn is eventually in every neighborhood of x. In the bracket I have written, be careful about the definition of eventually and read it again carefully. So next example I have given that this. As n tends to infinity, that means I told you the behavior of the sequence basically depends on how it behaves at the infinite level. Look, as n tends to infinity, it goes to 0. So my guess is that xn.
No, sir, 1.
1. Okay, I have forgotten to give you a definition. When I say that xn going to this converge, then we write also this notation. Xn goes to x, or we write this. Sometimes we write n tends to infinity, but I'm saying this is not required actually. The old books, old authors, they write that. Limit xn means here the limit is only with respect to this thing. Okay, because actually this means this theoretically. So this is not required. Okay, these are the notation. Don't confuse the notations with symbols. Notations are the convenient tools to express the things. So xn converges to n, 1 by, then you can see that. Look, 1 plus 1 by n minus 1 equal to coming 1 by n. Okay, so that you look here, if you have this, want to make it less than delta, that means you'll have to choose n greater than delta. That means if you take the neighborhoods, that here x equal to 1, so that you have 1 minus delta, 1 plus delta. So that if you want to push it here, the members after a while, everybody, that means your n has to be greater than delta. It's like if you take delta equal to 1 by 10, then again I told you that. Then after starting from 11, everybody will be here. Look, I have taken previously, the previous example and this example basically same for discussion. There I have taken xn equal to 1 by n. Here I have basically shifted, translated. There it was 1 by, this is 0. This is 1 by n, suppose, and this I have translated, shifted 1 plus 1 by n. Okay, so that there is no, basically there is no difference between these two sequences. I just shifted by 1 everything. So here it will converge to 0, and here it will converge to 1. But otherwise the discussion will be same. Okay, got it?
Sir, n should be greater than 1 by
What?
delta.
I didn't understand it.
N should be greater than 1 by delta.
N greater than?
1 by delta.
N greater
You
than
have
1 upon
plot.
delta.
Greater than 1 by n. Oh, hello, what are you saying?
N
Hello?
greater than 1 upon delta.
N greater than 1 upon delta. Huh? So what are you
Yes,
saying?
sir. Sir,
Oh,
जिसको
acha,
ये
acha,
गोला
I have written here wrong. Acha. That's good. You're listening to me? Yes. Okay. Yes. Right. So that now the thing is that so behavior, so look, you have written this, that means what it actually informally, what is happening? That means after a while, xns, these xns members are getting sufficiently close. Sufficiently close, this thing, apparently vague word, that is close to x. Look, this sufficiently close, it will depend on how much you want xn to be close to x. How much you want basically. So that will depend on the neighborhood. Neighborhood basically tells you that look here the role of the neighborhood. Here neighborhood tells you that how much members of the sequence close to x. If you choose a small neighborhood, that means if you choose delta small, you say it is very close, then you'll have to probably you'll have to choose larger n. Okay, right? But ultimately they are close to x. But this you should know sufficiently. This is same thing as depending on the neighborhood. Okay, close. Now look, question is that I have defined this. Okay, next question is that look here, whether it is possible for a sequence converging to x and converging to y also, where x not equal to y. Okay, where x not equal to y. Look, I have given the proof. You can see that this is a simple application of triangle inequality. But look, from the figure, it is immediate. Suppose x not equal to y. I can assume x less than y. It doesn't matter. Two numbers, one number will be less than other. Suppose this is x and this is y. Now we take 2 delta equal to, here I have written 2 epsilon, y minus x. So basically, theoretically, you will take this. That means it doesn't matter then which one is bigger, which one is smaller. Okay, then that makes sense. Here I have taken. Now that means this. This is your, look, this is x plus delta equal to y minus delta. It's coming. You can take in 4 parts also. And now look, if I say this is converging to x, this is converging to x, that means, look, this is x plus delta, this is x minus delta. And this is here, y plus delta.
Plus delta.
This is equal, I have put that. X plus delta, y minus delta, right? But open interval I am taking. Okay. Now look, if this happens, eventually every member of the sequence is here, or eventually it is also here. But eventually say it may be for all n greater than equal to n naught. It is for all n greater than equal to m naught. So I choose the maximum of that. Okay, right? So that eventually they will be here, eventually they will be here. But these two neighborhoods are disjoint because even this is an open neighborhood. Okay, so that is not possible. That eventually means infinitely means after a while only finitely many will be left out. They are here. Even again only finite will be left out. They are here, but they are disjoint neighborhoods. Okay, so that is not possible. That exactly in the proof. The proof says that, but pictorially it means this. So that means if a sequence converges, that this limit has to be unique. Look, previously I was taking a limit actually, x. Now I call it the limit because limit is unique. Okay, right? Got it? So that you should look at the proof. This is nothing. That is the same thing I did. I took 2 epsilon and this and triangle inequality. It has to be a contradiction. Okay. Now look here that the unique limit xn goes to x and that. Now look, if you have a starting with a sequence, now I would like to tell you that that given a sequence, you have 2 possibilities: either converge or do not converge. Does not converge or converge. Okay. Now let me tell you that now the sequence, if you somehow say if it doesn't converge, your life is over. That your question is over. You don't need to bother about it. But the point is that somehow you figure out it will converge. Now look, here you can be asked two questions. First, if you said whether sequence converges or not. If it doesn't converge, it's fine. But then if it converges, now look, if it converges, then converges to what? Which x? I have picked up the very simplest example, that this. Okay. So that now look, so that you should be careful about. Given a sequence, First of all, whether you are asked this or asked this, because this is easier to do it than this, So if you are asked to see that whether the sequence converges or not, then don't go to this first, because this may be difficult. Because if it doesn't converge at all, then you'll be wasting your time. That looking at whether it is converging to a point, trying that. So that if first of all, you should figure out whether it converges or not. And converges, these two questions are different actually. This is easier, this is little bit difficult. I am saying I can give you a sequence which converges to root 2, but it is not immediately clear that sequence converges to root 2. Okay, got the point? So that be careful about the question. How will you try it? Okay, I think, let me tell you that I have given this example also. That let me see that here. I think this is the example. Page 28, number 16. Okay, look, this problem is saying first show that it converges and then determine its limit. Look here how it is defining. It's defining x1 equal to 1. It is called the inductively yet defining. And xn plus 1. Look, this way I can always define a sequence. First I am defining x1 equal to 1. Then I can define x2, putting x1 here equal to 1. That means x2 will be 1 by 4. Then I define x3. This is called the, you define inductively. Look, it is not I am doing infinite process. Suppose xn has been defined, then I can define xn plus 1. I have given already x1. So it is in two processes, 2 steps. x1 is defined and then xn plus 1 is defined. And then you use induction. And here he is saying show that it converges and determine its limit. Okay. Determine to limit, if it converges, it will have a limit. That will require some extra work, that you can see that. Okay. So that now the thing is that you may ask, without checking this, how will I say that it's converge? Okay. Well, now look, here I am giving you this. If a sequence converges to x, first of all, I may not know which is x and that. That means actually what? This is x. Whatever neighborhood we are picking up, that means what? The members of the sequence, they are also getting close to each other. That means given a neighborhood x minus delta to x plus delta, there exists a knot such that, look what I'm doing it, xn minus xm less than delta for all nm greater than n0. That is, after a while they are getting close to each other. I do not know, here is a difference, that they are getting close to which point. All I know, they are getting close to each other. Okay. Question is, does it imply this condition? Does it imply that xn converges? Here my thing is little bit different. Understand? Okay. Little bit different. Okay. So think about this. I'm getting close to each other. Okay. So that if they don't get to close each other for a while, then you can say it doesn't converge. It doesn't converge. Okay. It doesn't converge. But if you say it is always true, then suppose this question is affirmative, that it converges, then actually this is a good tool if you are just asked whether sequence converges, not necessarily to ask, they ask you to find the limit. That question number 16 asked to find the limit, but they could simply say find out that whether the sequence converges. Okay, so this is one condition. Later on we'll talk about this. Is called the Cauchy criteria. Cauchy criteria. But before that, I should have something simpler, that to find out whether the sequence converges or not. Like now look here, that is the bounded sequence or not. Look, a bounded sequence by definition is very straight. That means suppose xn is a sequence, it is called bounded. It's called, I have gone to my next note actually. It's called bounded if there exists m greater than 0 such that okay, that means it will be in this interval. That means everybody of the sequence, every element of the sequence must be inside this interval. Now look, if you have a convergent sequence, except finitely many, if you choose any neighborhood, particularly look, suppose xn converges to x. I can take x, just convenience, x plus 1 here and x minus 1. Okay, so that everybody after a while for all n greater than equal to n naught, xn minus x is less than 1. So outside you are having this thing x1, xn naught minus 1, and here you have this x is less than equal to, sorry, less than even. Sorry, here is xn ठीक है, for all n greater than equal to n. So you choose max m equal to max of this. Up to then choose the max of all these things. This is the thing, idea. Then you get sequences bounded for all n. So the outside these are left out. So you choose the maximum of that. So look, I am choosing maximum. For inside it is less than this. For outside you have these numbers. I am choosing the maximum one. Okay. So this is this. So that means every convergent sequence is bounded. So that every convergent sequence, this is a necessary condition. Every convergent sequence is bounded. So if I ask you to see, here is the checking thing, that whether a sequence is convergent or not, first to check whether it is bounded, because if it is not bounded, then obviously don't be convergent, because it has, like if I give this simple sequence, of course this doesn't converge, because this is not convergent, because it is not bounded. It is not bounded. But you should know that a bounded sequence may not converge. A bounded sequence may not converge. Look, if I take this, minus 1 to the power n. Look, sequence, the members of the sequence are coming actually minus 1, 1, minus 1, 1 like this. It's repeating basically. But that means it is bounded by this. Norm of x1 equal to 1. So it is a bounded sequence, but it doesn't converge, because many members of the sequence, they gather around 1, and many members of the sequence also gather around minus 1. So the xn here doesn't converge. Okay, so that if it is not bounded, immediately you don't need to do anything. You can say it is not convergent. So the first thing you should check when you are asked a question whether it is convergent or not. But first check whether it is bounded at all or not. But then next lecture I will talk about this. Now look here, I said bounded sequence, the behavior of sequence. Have you noticed this? Here it doesn't converge, but I get two subsequences. One subsequence converges to minus 1. Look here, if I take the odd numbered elements, that give you the subsequence x and k equal to minus 1. Okay, when k equal to, k is a function, nk, k is coming. That actually, sorry, I have taken the n right. K is 1, 3, sorry, 5 this, and x and k writes to z and k equal to 1 if k equal to 2, 4, 6 and that. We are getting two subsequences, and this subsequence x and k converges to minus 1 and z and k converges to 1. Okay, now you are getting that. Now you may have a natural query. A bounded sequence may not converge, but then since it is bounded, is it possible they'll have to gather around? We may have more than one point. What I'm saying, does it happen that there will be some points y1, maybe infinitely many or finite, something another point than that, such that many members of the sequence gather around y1, many members of the sequence gather around just yk like that. Okay, that means it's called subsequential limits. Actually, subsequential limit means limit of a subsequence of that sequence, limit of a convergent subsequence of that sequence. The question is a bounded sequence. Look, it's an example. Whether for a bounded sequence, is it true that I must have subsequences and I must have some points around which those subsequences will converge. That means actually you should understand that given a sequence, if it is convergent, it is the nicest behavior you can expect for a sequence. If a sequence is convergent, then that sequence is the nicest. You can't expect more than from a sequence than being convergent. But if it is not convergent, so that nice things so you've got, but if it is not convergent, the question is, if it is not convergent, then your questions naturally will be that how good is it or how bad it is. Okay, convergent sequence is the nicest sequence you can have. Think of that. That means if you do not have a nice sequence, then then you'll have to figure out basically how much it is nice and how much it is not nice. Look, this sequence though doesn't converge many places, this will be still useful sequence, but still it is a nice sequence because its behavior is very nice. It gathers around 2 points, minus 1 and 1. Okay. On the other hand, if you see that a sequence, it is not gathering the elements around any point on that. Okay, it is not gathering. That you can think of an example. It is not gathering around in, look, sequence xn equal to n. In the real line, I have not talked about extended real line. It doesn't gather around any point. So it's a bad sequence. You can see this is unbounded sequence, so it doesn't converge. But even then, you see that even the members of subsequence, that means you don't get a subsequence gathering around a point. So that means it's a pretty bad sequence. Pretty bad sequence. Look, this sequence doesn't converge, this sequence doesn't converge. but there is a difference. It doesn't, its members doesn't gather around any point. Infinitely many members doesn't gather around any point. Where here the members of the sequence gather around actually 2 points only, +1, -1. So this is still way better than this sequence. So next thing is that what do we have? Want to handle tomorrow, that that basically to figure out, look, this idea, the gather, we call it cluster. That how the members of a sequence, particularly bounded sequence, unbounded sequence, you can figure out that they won't gather around any point. They won't gather around any point. Okay, if it is unbounded, because if it is you can check that why it won't be that. Okay, that you should check. Of course, qualify, not for all unbounded sequence. Look, let me tell you that. If I take xn equal to n, now if I change the sequence a little bit, 1, then I take 1 again, then 2, then 1, then 3. This is the way I'm giving the sequence. No new sequence. Now look, that means 1, 2, 3. This is unbounded because it is also unbounded. Okay, but here you have got a subsequence which is gathering around 1. Okay, right? This is a trick. Okay, so that here bounded sequence. So basically, we try to see the difference between bounded sequence and unbounded sequence. That means we try to see that around which point infinitely many sequence. I always say that its behavior ultimately depends on this thing. Infinitely many members of the sequence gather. Clusters. If you have such a thing, this is called a cluster. These are clustered. Okay, so I'll talk about this cluster point tomorrow. It's fine? Any question? Hello? I'm asking any question?
No, sir. Clear.
What
No,
question?
No, sir. Thank you, sir.
Clear.
But make sure that you read the notes, try to understand the sequence, because next week probably I will try, as soon as possible, I will shift to metric space. And there all the time you'll have to be comfortable in handling sequences. Okay, so that make sure that you understand, you read sequences very carefully. If you have difficulty in understanding sequence, rather in understanding the behavior of sequence, you will be in trouble. Okay, you will be in trouble next semester also in major.
Yes, sir.
Okay, make sure that. Okay,
Yes, sir.
see you tomorrow. Bye.
Thank you, sir.
Thank you, sir.
Yeah, you are welcome.